In this class, we continue the discussion on the complementary slackness, and we try to explain how the simplex table is able to capture the complementary slackness. In the last class, I gave an example where I said we took two feasible solutions to the primal, one of which happened to be the optimum, and I mentioned that in the solution, for the same example, in the solution that was not optimum, the corresponding dual became infeasible, whereas the one that was optimum, the corresponding dual was feasible, from which we said that the solution is optimum. Now let us go back to the same example, revisit the simplex table for this problem and try to understand what the simplex algorithm is actually doing. So let us start with this. This is the simplex table. Instead of x3 and x4, we have introduced u1 and u2. So you will have x1, x2, u1, u2 as the variables, and then we start with u1 and u2, and then x1 comes into the solution replacing u2, and then x2 comes into the solution replacing u1, and we have the optimum solution with x1 equal to 3, x2 equal to 4, and objective function is equal to 66. Let us now start looking at the simplex table also with the dual in mind. So if we write the dual to this problem, initially let us assume that you will be having inequalities. Therefore there are two constraints. The dual will have two variables, y1 and y2. The two constraints give us two slack variables, u1 and u2, which are mapped to y1 and y2. And there are two variables in the primal which will give rise to two constraints in the dual, and they will have minus v1 minus v2, where v1 v2 are the slack variables. So the dual will have y1 y2 and v1 v2. Complementary slackness also tells us that there is a relationship between x and v and y and u. So xv equal to 0, yu equal to 0. So what we do now is we just map the corresponding dual variable to the primal variable, remembering that the two primal variables x1, x2 resulted in two dual constraints which resulted in two dual slack variables. So primal decision variable is mapped to the corresponding dual slack variable, x1 is mapped to v1, and so on. So also u1, which is the primal slack, is mapped to y1, which is the dual variable. Now let us start doing this. The first simplex iteration is with Cj minus Zj equal to 10 here, Cj minus Zj is equal to 9 here, 0, 0, and we realize that this 10 actually entered the solution. The 10 entered the solution. We did 7 by 3 and 6 by 4, and then 6 by 4 actually left. Now let us try to understand what is actually happening here through this. So the first iteration, we had x1 equal to 0, x2 equal to 0. From the solution, u1 is 21, u2 is 24, implies x1 and x2 are non-basic. We can see that x1 and x2 are non-basic, u1 is 21, u2 is 24. Now let us apply the complementary slackness conditions for this solution. Now if x1 is equal to 0, then v1 is in the solution, x2 is equal to 0, v2 is in the solution. u1 and u2 are in the solution in the primal, therefore y1 and y2 are 0. So one way is to go back to write the dual and then try to solve the dual with v1 and v2, solving the dual for v1 and v2, keeping y1 y2 is equal to 0. If we do that, we will get v1 is equal to minus 10 and v2 is equal to minus 9. If we do this, we will get v1 is equal to minus 10, v2 is equal to minus 9. If we write the dual and put values y1 and y2 equal to 0. But let us look at what the simplex table says. Now the simplex table shows a 10 here and a 9 here. Now, the negative of the Cj minus Zj seem to show the corresponding dual solution. Now, if we realize this, if you see u1 is in the solution in the primal, so y1 has to be equal to 0. We have now mapped y1 alongside u1, go down, here you get a 0 here, you get a 0 here, this is the y1 solution. Similarly, u2 is in the solution in the primal, by complementary slackness y2 u2 is 0, therefore y2 has to be 0. Now y2 is mapped to u2, so this is the value for y2, y2 is 0. That is precisely why the Cj minus Zj for every basic variable has to be 0, because when that variable is basic, the corresponding variable in the dual will be non-basic and it will take the value 0. Now we realize x1 is equal to 0, non-basic in the primal, its corresponding dual variable v1 is actually basic and has a value minus 10. So negative of the Cj minus Zj is able to show the dual solution. Similarly, x2 is non-basic in this solution, x2 is 0, so x2 v2 is 0, we realize v2 is minus 9, which is this which we would have obtained otherwise by applying complementary slackness. So right here in the very first iteration, we are actually solving a feasible solution to the primal with u1 equal to 21, u2 equal to 24. This is not only feasible, but it is basic feasible. And through the Cj minus Zj values, we are actually evaluating the dual solution. Now the dual solution is y1 equal to 0, y2 equal to 0, v1 is equal to minus 10, v2 is equal to minus 9. Now v1, v2 are infeasible. So we look at the Cj minus Zj and enter that variable with a positive Cj minus Zj. Now let us say we do one more simplex iteration, after which we get x1 equal to 6, u1 equal to 3 with z equal to 60. Now let us see what happens to that. Now our second iteration is x1 equal to 6, x1 equal to 6, u1 equal to 3. So when I substitute x1 equal to 6, u1 equal to 3, x1 equal to 6 here will give u2 equal to 0, x1 equal to 6 and u1 equal to 3 will also give me x2 equal to 0, and it is fairly obvious that u1 x1 are in the solution, u2 x2 are 0, they are non-basic with 0. So this is the primal feasible solution, primal basic feasible solution. Now let us apply complementary slackness. When u1 is in the solution, y1 has to be 0, so y1 is mapped to u1, you will realize y1 is 0. The Cj minus Zj of a basic variable is 0. x1 is in the solution, therefore v1 has to be 0, therefore you see under x1 v1 is mapped, v1 is 0. Now if we apply the complementary slackness with y1 and v1 to 0 and we write the dual and we solve for y2 and u2, we will get y2 is equal to 5 by 2, v2 is equal to minus 3 by 2. So go back and see that 5 by 2 is shown as minus 5 by 2 here, as I said negative of the Cj minus Zj, and this 3 by 2 is shown as the minus 3 by 2 is shown as 3 by 2, which is the negative value. So again what we do in this iteration is we are looking at another feasible solution to the primal with x1 equal to 6, u1 equal to 3, and we are evaluating the corresponding dual solution. The corresponding dual solution is still infeasible because y2 is positive but v2 is negative, negative of the Cj minus Zj. So v2 is negative, v2 is negative, therefore it is infeasible, and therefore we look at Cj minus Zj again. This variable comes into the solution. We now realize that this variable is coming into the solution with a positive Cj minus Zj, and then we do one more iteration and finally get x1 equal to 3, x2 equal to 4. When x1 equal to 3, x2 equal to 4, automatically u1, u2 are 0, and you realize that u1, u2 are 0. So x1 equal to 3 implies v1 is equal to 0, So, V1 is equal to 0, x2 equal to 4 implies V2 is equal to 0, and when we put V1 equal to 0, V2 equal to 0 into the dual and we actually solve, we will get y1 equal to 2, y2 equal to 1. Negative of the Cj minus Zj, so y1 equal to 2, y2 equal to 1 is actually feasible to the dual, and therefore it is optimum with 66. Now you realize that is shown here. So in the iteration 3 you realize y1 equal to 2, y2 equal to 1, it is optimum. So negative of the Cj minus Zj is actually the value of the dual, and under u1 u2 you will be able to see the value of y1 y2 with a negative sign. So 2 and 1 is the solution. So what does simplex algorithm do? There are two ways of looking at the simplex algorithm. The first way is simplex looks at a basic feasible solution to the primal, evaluates Cj minus Zj as a way to check whether the objective function can be further increased. So with 10, 9, 0, 0 it can be further increased. With 0, 3 by 2, 0, minus 5 by 2 it can be further increased. But with 0, 0, minus 2, minus 1 it cannot be further increased, therefore the optimum is reached. That is one way of looking at the simplex algorithm. The other way of looking at the simplex algorithm is I evaluate a basic feasible solution to the primal. Through the Cj minus Zj and the negative values of the Cj minus Zj, we look at minus 10 and minus 9 as the dual solution. Dual is infeasible. So when the dual is infeasible, and you can see that the dual slacks are 10 and 9, which means there is a gap in the dual solution. For example, the first solution would be from the dual it will be 3y1 plus 4y2 greater than or equal to 10. So y1, y2 are 0, therefore V1 becomes minus 10. So there is a gap between the left hand side and the right hand side of the dual constraint. When a slack variable takes a negative value, V1 takes a negative value, V1 has to be greater than or equal to 0, but if V1 takes a negative value, one of the constraints is violated and there is a gap. Now here both the constraints are violated. Now we try to make the dual feasible by bridging the gap. Now this is the variable that has the most negative value, V2 is minus 10, where the gap is large and the violation is large, which has resulted in a positive Cj minus Zj of 10. So entering a positive Cj minus Zj is the same as making an infeasible constraint feasible, making an infeasible dual constraint feasible. So x1 comes into the solution so that this V1 that is negative will try to become 0 in the next iteration. So primal non-optimality, or one way of saying a positive Cj minus Zj indicates non-optimality of the primal. So most positive put it in. The other way is to say a positive Cj minus Zj indicates infeasibility of the dual because the negative of the Cj minus Zj is the dual. So here there are positive Cj minus Zj's indicating non-optimality. Here there are positive Cj minus Zj's for the x2 indicating non-optimality. Here there is no positive Cj minus Zj, therefore optimum. The same thing is told differently. Here the dual is infeasible, so bridge the gap by pushing the one that has the largest gap. Here the dual is infeasible, bridge the gap by pushing V2 into the solution so that V2 from a negative value will become 0. Now here the dual is feasible, therefore it is optimum. So simplex does the same thing. In a single solution it actually solves the primal as well as the dual to a given linear programming problem, and that can be best understood if we look at complementary slackness conditions. Now let us look at some more aspects of the primal and the dual. Now we start something called the economic interpretation of the dual. Now what is the meaning of the dual? Does it have a meaning? How is it related to the primal? Is there an economic angle? Is there a money angle, a monetary angle to looking at the dual? So, let us start the economic interpretation of the dual in this class and continue as we move along. So, again we use the same example to illustrate, so that we can have a better understanding of linear programming, because we have seen this example so many times already and we will continue to see it for some more time, but we can understand a lot more things by keeping the same example. So, we know that primal, we know the dual already, we know the optimum solution x1 equal to 3, x2 equal to 4, z equal to 66, u1 equal to 0, u2 equal to 0, y1 equal to 2, y2 equal to 1, etc. Now, what is the first thing we understand? Now, from the primal, the revenue is 66. The revenue is 66. If you look at it, this is the problem with which we started. So, we make two products, there are two resources, these are the revenues associated with selling the product 10 and 9, and finally we solved to say make 3 of the first product and make 4 of the second product. Two types of sweets, so make 3 of the first product and 4 of the second product to get a revenue of 66. Now, what does the dual tell me? The dual says y1 is equal to 2, y2 equal to 1 with w equal to 66. Now, this w equal to 66 comes from 2 into 21, 42 plus 24 is 66 is one way of looking at it. The other way is 2 into this 21 plus 1 into 24 is 66. The right hand side of the primal is the objective function of the dual. So, before explaining what y1 and y2 are, we also understand that if y1 and y2 represent something, 21 and 24 are the resources with which we started the problem, and if y1 and y2 represent something, 21 y1 plus 24 y2 is equal to 66, which is the revenue that we got by selling the products and making this 66. So, the first understanding is, if 21 into something plus 24 into something is also equal to 66, then this y1 and y2 have something to do with 21 and 24, it has to do with the resources, and we now say that the worth of the resources is 66 at the optimum. It is also to say that if I have 21 units of the first resource and 24 units of the second resource as resources, and then I transform them into products and make 3 of the first product and 4 of the second product and sell the products to realize a revenue of 66, it means the actual worth of the two resources, which is 21 and 24 units of the resource, the worth of these two resources at the optimum is the same 66 that we have. So, the first interpretation is the dual variable values are worth of the resources at the optimum. We will qualify it a little more, but they are the worth of the resources at the optimum. It is also good to say worth of the resources at the optimum. So, first economic interpretation is y1 and y2, which are the dual variables, are the worth of the resources at the optimum. Now, let us understand a few more things about. Once again, let us go back to the same example. The original problem was 3x1 plus 3x2 is less than equal to 21 and 4x1 plus 3x2 less than equal to 24. Now, let us assume that we are going to solve the same linear programming problem. Instead of having 21 units of the resource, we are going to assume that we will have 21 plus delta, where delta is a small positive quantity. You can imagine 21.1 or something like that, a small quantity. What if the resource increases a little bit, 21 plus delta? We are also going to make an assumption that because of this increase of delta, we will still continue to make both the products, which means x1 and x2 that were in the solution, we know the solution, x1 and x2 were in the solution. We will assume that we will continue to make both the products, and under that assumption what will happen is, if we will assume that x1 and x2 will continue to be basic, we will continue to make the two products. Then it is enough to solve for 3x1 plus 3x2 is equal to 21 plus delta, and 4x1 plus 3x2 is equal to 24. Assume that delta is known. So, when 3x1 plus 3x2 is equal to 21 plus delta and 4x1 plus 3x2 is equal to 24, if we actually solve, we will get x1 is equal to 3 minus delta, x2 is equal to 4 plus 4 delta by 3, and when we substitute, the objective function will be 66 plus 2 delta. So, what does it tell me? It tells me that if I have a small delta extra in the first resource, I can now convert this delta into a product and finally sell these products, and the revenue instead of 66 will become 66 plus 2 delta. So, that is what this tells me. Therefore, if we increase the first resource by a small delta, the profit or revenue goes up by 2 delta. The worth of 1 unit of the resource at optimum is 2, which was the dual solution y1 is equal to 2. If you go back to the previous slide, we know that y1 is equal to 2. You see here that y1 is equal to 2, y1 is equal to 2. So, this is actually the worth of that resource. Therefore, you realize 2 into 21 plus 1 into 24 was 66. So, y1 is equal to 2. So, we realize that if we increase the first resource by delta, which is shown here 21 by delta, the thing goes up by 2 delta, 66 plus 2 delta. So, therefore, this 2, which happens to be the value of y1, is the marginal value of the resource at optimum. Now, at the optimum, if I increase the first resource by a small delta, then the profit goes up by 2 delta. Therefore, the worth of this resource, the marginal value of this resource, the worth of this resource at the optimum is indeed 2. We will see some more aspects of the economic interpretation of the dual and then move on to the dual simplex algorithm in the next class.